But also let me know when you've got everyone admitted. Can you hear me? Okay. And can you hear me, my voice? Okay, great. So hello, everyone. We're going to get started. Thanks so much for joining us tonight. We have a fascinating program for you. I'm very excited about it. For those of you who may not know me, I'm Steve Wishner. I'm the New England Region Board Chair. And I'd like to welcome you to the Boston Business Council meeting for tonight. I just returned a couple of days ago from several months in Florida, so I am freezing my various body parts off right now. So I'm delighted to be back in Boston, but I wish the weather were a little bit more like Florida at the moment. So tonight we have one of Technion's rising stars, Assistant Professor Assaf Zinger, as our guest speaker. Thank you so much, Assaf, for joining us. This is great. I'm going to hand the mic over to Jeff Holzer, who is the co-chair of our Boston Business Council, who will introduce himself and the speaker and get things rolling for us. So take it away, Jeff.
Thanks, Steve, and hi, everyone. The Boston Business Council meetings have been a staple of the American Technion Society's presidents from England for many years. These meetings bring educational programming from the Technion to the greater Boston and New England communities free of charge, providing a wonderful opportunity for learning, networking, and connecting virtually and in person. As new to this position, I look forward to getting to know everyone better, and I welcome any thoughts, feedbacks, and recommendations as I begin working with Greg Rutfield to bring you great speakers from the Technion. We are fortunate tonight to have Assistant Professor Assaf Zinger with us. Assistant Professor Zinger is a rising star in chemical and biomedical engineering and nanotherapeutics. He received the Allen Fellowship for the integration of outstanding faculty and is a member of the Global Young Academy. He is an adjunct assistant professor at the Houston Methodist Academic Institute, and he is also a Technion faculty ambassador. Recently, Professor Zinger was invited to join the prestigious Lindau Nobel Laureate meeting as a young scientist. Professor Zinger received his bachelor's degree in biomedical engineering from the Technion and also received his master's and doctoral degrees from the Technion in Associate Professor Abby Schroeder's laboratory for targeted drug delivery and personalized medicine technologies. It's a great pleasure. I'd like you all to welcome Professor Zinger.
Shalom, guys. What a pleasure to be here. And let me start with Go Celtics. Can you please win tonight? So I think Philadelphia doesn't need any more wins, so stop giving them the opportunity. So thank you so much for having me. Let's do it as a conversation because I will provoke you. I don't know if you heard me in the past, but I like to ask my audience questions. So if you won't answer, I will stop and wait and ask again. I prepared several stories for you, so feel free to ask in any point. Just raise your digital hand in Zoom. I'm a multitasker and I have ADHD, so I'm doing tons of things multiply, so please try me. Send me text messages as well. A bit about myself. So right now I'm in San Palo Alto, Los Altos. I flew on Saturday to Los Angeles from Tel Aviv, 2 days in Los Angeles, 2 days in Arizona, Phoenix, and I have this morning to San Francisco, going back to Israel, and again to New York, and again to Boston, and again to Israel. My wife will kill me. So I'm last generation in Israel, born and raised in Tzfat. I'm a mixed dog of genes. I have my father's side are Holocaust survivor. They escaped the Nazis from Transylvania. My mother's side is Tunisian that escaped the Nazis from Tunisia. But the other side of the family, my grandfather, he's 7th generation in Tzfat. I'm married to a Moroccan Egyptian lady by the name of Noah. So if you need O positive blood, just text me. I'll be happy to donate it. At the age of 18, I was recruited to the Israeli Defense Force. I served as the tank commander, and then during the Second Lebanon War, I was the operation officer of Brigade 188, that one in the south part of Lebanon. After the war, I was promoted to be a company commander and decided that I want to leave the army after I finished my duties with honor. However, the army in Israel don't release you very easily, so I'm still serving in reserves. I'm now a major, next year Lieutenant Colonel. I'm the Armored Corps Executive Officer in Israel. And hopefully we can do things better, not only in peace-wise, but also in scientific issues. After the army, I decided to study to be a physician or an electrical engineer. I did not know really what I want to do, so I studied biomedical engineering at Technion, master degree chemical engineering, and a PhD biochemical engineering. And my postdoc was in Texas, Houston, Texas. So howdy y'all. My daughter was born in Texas, one of them. So she's a citizen. And if one day she will want to be your president, you guys are in big trouble. I will share my screen. If you have any questions, please do whatever. If I'm speaking too fast, or if my Hebrew or Southern accent is confusing, please don't hesitate to ask questions. So can you see my screen? Perfect. So the first story is about pancreatic cancer. Pancreatic cancer is the most lethal of all cancer. Sorry for interrupting. Sally, how much time do we have?
Take as long as you like.
As
We
much time
generally
as you need.
end around 8:30, but take
Oh
what
no, you tell
we have.
Israeli
We leave
take
time
as
for
much as you
Q&A
need.
though.
Okay, forget about the game tonight, guys. No, I'm kidding. 7% 5-year survival rate and fourth leading cause of cancer-related death in the United States. That's a horrible statistic. And I don't know if you had the chance to look at pancreatic cancer, but this is how healthy pancreas, healthy actinic cells look like. And this is how the tumor looks as well. You can see my mouth, right? And if no, I'll switch it to laser. Now you can see my mouth. So this is a solid tumor in the pancreas on your right. This is another islet of tumor, and this is another tumor. But if I were to ask you guys, what is the difference between the two samples? So it's pretty easy. You'll tell me, hey, you have lumps on the right and you don't have lumps on the left, or maybe small lumps, which are kinds of something else. But if you will take a microscope and literally look inside into the depth of the pancreas, you will see something very clear. Does one of you want to take the chance and tell me what is the clear difference between the diseased pancreas to the healthy pancreas? 0 volunteers. I'll tell you, it's pretty easy. You can see it. Steven, you are smiling. Take the shot.
Well, I don't know what they are, but obviously those blue streaks.
Awesome.
Are
I'm looking for
problematic.
postdoc. Come to Israel. I'll recruit you tomorrow. So these blue fibers are collagen fibers. This staining called Masson trichrome staining. And this is how we stain collagen fibers. If you will look at your right, at the diseased pancreas, it's clearly that a high dense collagen matrix formed inside this tumor compared to the healthy pancreas on the left. This is some kind of tendon. If you will touch your Achilles tendon in your leg, this is how this kind of tumors feels like. This is the result of a desmoplastic reaction, which is an immune reaction caused by the tumor. And this is very rigid because this is how tendons feel like. If you eat a steak, Texas I mentioned, with tendon, it's hard to bite, right? So this dense collagen matrix basically causes pressure on the blood vessels that supply blood, nutrition to the tumor, but not only. It also prevents chemotherapy to penetrate. Literally, it squeezes the blood vessel. And when we injected drugs and calculated the differences in the density of the tumor compared to the healthy tissue, it was 12.25-fold different. And you can see the diseased tissue versus the healthy tissue. And this is literally the border. And Israeli, we know a lot of this. So we can clearly see the difference between healthy and diseased tumor. So we injected the drug. And this is how the tumor looks like. And as I mentioned the stakes before, the white thing is the bundle, the collagen binder. And again, if you push it, it's very rigid. And as you can see, less than 2% of the drug reached the tumor, which is actually proof the fact that chemotherapy cannot penetrate. And then something happened. After understanding the drugs cannot reach the tumor and wasting 2 years of my life in my PhD, in 2014, protective edge operation, the Gaza war, as you call it, started in the South. So I got a phone call. I did not have a beard and I was 10 kilos thinner, but I went to the South with my Kevlar and my helmet, left this project and literally met my unit in Gaza. And then I talked to my deputy, Chagai, which was a captain. Now he's a major. Last year we ranked him the major rank as well. And I told him, Chagai, I have an issue. There is a tumor bunker I cannot penetrate. What can we do? And did not have an idea. In this time, Hamas did for the first time tunnels. They started to dig tunnels in Gaza, like Vietcong did in the Vietnam War. And what happened that, you have this eureka moment, like midnight on the dune, that if these bastards can drill holes, we can do it as well. And in a second, I'll show you what we did next to it. But another something I want to emphasize is how many Technion students serve in the army. So I'm taking my Jeep and my tank and going inside the border there, and suddenly you start to recognize, Tzvi. Tzvi is a chemical engineer student. This is, when I told him to put his Kevlar, he did not want to put his Kevlar, so I called his wife. I told her, hey, your husband does not want to put a Kevlar. 2 seconds after it, he put the Kevlar helmet and went into the tank. But basically, a lot of technical students were all over the place. And after sitting almost 1.5 months in Gaza, very basic things were missing. Underwear, toilet papers, wet papers, a speed stick, toothbrush. So what I did, I literally called the president of the Technion back there in the days, Professor Peretz Lavi, and I told him, Peretz, I don't know how you're going to do that. We need this stuff. So Peretz called the American Technion Society, and I think this is the hat I gave back there in the days. They had a really nice swag. We need to work on the swag again, Sally. But we got basically in less than several days, tons of toothpaste, speed stick, wet towels. All our colleagues who did not serve in the front basically went to package for us. I took one of the Jeeps in my company, sent it to the Technion, and brought a truck back to Gaza and actually deliver this kind of packages to each of the Technion students we met there. Each of them got this kind of packages with a note, say, hey guys, continue the good job you are doing and come back home safe. And I think in this day, I fell in love with ATS because they helped me and my brother in arms doing this thing. And I'm going back now to the science, I'm sorry, but that's a very personal message. So this Hamas thing really did a eureka moment. And when I came back to my lab, I decided that I'm going to develop Hamas nanoparticles. Don't tell them that, but if they can dig tunnels, I can dig tunnels in the tumor. So what we've done, I literally created this bunker buster nanoparticles that can drill holes in the fibrotic tissue, allow chemotherapy to penetrate. How did I do that? So I took collagenase, which is a collagen disassembling enzyme, and encapsulate it inside the nanoparticle. It's like an Uber driver, an Uber taxi, right? It takes you whenever you want. And why did I encapsulate it? Because if you will inject collagenase systemically, it will go all over the body. It will start disassemble tons of stuff. However, if you put it in a nanoparticle, it targets specific the pancreatic tumor, cannot penetrate though. But when it's being released, suddenly small holes are being formed. And this is what I thought at the beginning that will allow chemotherapy to penetrate to the tumor. And this is what happened. So you see here a pancreatic tumor, that's a biopsy that was taken, and we evaluated the amount of fibrosis, the same dense bunker I mentioned. And this is like the amount of fibrosis after soaking it with the Hamas nanoparticles, right? And this is a healthy pancreas. So basically by using this pre-treatment of Hamas nanoparticle, we reduce the burden of the collagen fiber by 3-fold. And it was awesome because what we did next, we developed a preclinical model. So you will see in a second the pancreatic tumor in red. We injected the Hamas nanoparticles in 2 consequent days, followed by chemotherapy, and look what happened. So these mice were treated only with chemotherapy for 14 days. You can see how the tumor propagates. You can see how the abdomen is full with liquids, which is a clear sign of metastasis. However, look at the test group. We managed to decrease and almost, I don't want to say heal, that's a hard word, and almost cause the tumor to disappear using this pre-treatment approach. And that was like, hey guys, we can treat pancreatic cancer in mice, and I want to emphasize it, and I will explain why it's not in human until now, using this pre-treatment of the Hamas nanoparticle. And I think this multidisciplinary thinking together with the mandatory military service that any Israeli citizen need to do is a really good example how, the Jewish mind can literally sit together and develop new technologies to maybe make a huge impact, not only defense-wise, but only clinic-wise. Okay, I'm running a bit fast, but this paper was published in a very high prestigious journal. I think it's one of the most cited papers my team has. It's basically changed the paradigm regarding how we treat kinds of solid tumors in our body, not only pancreatic tumors. I think North Carolina, Chapel Hill, MIT, Harvard, UCLA, Caltech follow this kind of line and develop their other technologies followed by this enzymatic encapsulation inside the nanoparticles for treating solid tumors. So this is my first story. If anyone has a question,
Asaf, can I
Tim,
ask you a
now,
question?
please.
This technique obviously did a great job of reducing the tumor. Is that a permanent reduction, or after some period of time, and if so, what period of time, does the tumor regenerate again?
So Stephen, thanks again for a great question. We did it only for solid tumors that were developed for 4 weeks consequently. Hadar, I see your hand. In a second, I'll give you the freedom to speak. Sorry, not the freedom, the option to speak. You have the freedom. It's America. You can do whatever you want. And basically, we did not check it, but we did check the metastasis point of view. So I jumped on it, but thank you for bringing it back to that. So metastasis basically occur when cells from the solid tumor become systemically circulating and establish solid secondary tumors in other places in the body. And this was one of the major concerns the physician I worked with aroused. And I told him, you know what, you are right. So what I did, I collected this kind of tumors and I calculated the volume of the holes I'm making. The diameter of these holes that the Hamas particles are causing is 300 nanometer. Cells are 20 microns and bigger. So basically, we managed to demonstrate that we don't cause metastatic disease, after our pretreatment. Will it occur? We never checked it in mice. Hadar, please.
So are all solid tumors made of collagen? So it wouldn't matter where the cancer is?
So unfortunately, the answer is no. And I will tell you even more than that. The density of the collagen I showed you in one pancreatic tumor will not be the same in the other one. However, this mechanism of fibrosis is very known in pancreatic cancer specifically. Melanoma, for example, is known for more of liquid kind of tumor, not a solid tumor. Glioblastoma is a hybrid. So unfortunately, not all the tumors are characterized by high dense collagen matrix, but for pancreatic ductal adenocarcinoma, which is a part of pancreatic cancer, there is other pancreatic cancer, which is more healable, by the way. This is one of the main characterizations. Thank you, Ada.
Thank you. I lost my nephew last October to pancreatic cancer.
I'm sorry to hear that. My
Yeah,
condolences.
it was miserable. Thank you.
That's a horrible disease. That's a horrible disease.
Yes.
And you know, we all know Steve Jobs. We all know what happened to him with pancreatic cancer. And unfortunately, pancreas is something we cannot transplant yet. And this is part of the things my group is now working on. How can we make an artificial pancreas? But that's a huge challenge. That's a huge challenge that's standing among of us. Because, you know, if it's a liver thing and it's a liver kind of tumor and we detect it early, we can basically dissect this part of the lobe and if needed, we can transplant, which is not that easy, but it's doable. If something happened in the kidney, we can skip one kidney, right? Everybody knows that you can manufacture function normally with only one kidney. Okay, other question, or you are ready for the next slide? Perfect. So in this stage, my PhD is done. Nanotechnology was developed by giants before me. Bob Langer in MIT, which you probably all know and invest in his companies. Gabizon and Bernholz from the Hebrew University, Schroeder, Danny Pierre, so on and so forth. Marcel Makhlouf, of course, is stand behind us as well, with us. And the main problem of nanoparticles become the specificity. So I have to give a bit of background. If a breast cancer patient arrives to the oncology department, the first line of defense this patient is getting is doxorubicin. It's an awful chemotherapy that's been injected systemically in specific regime, minimum of like half a liter systemically. Just imagine how much poison reach to the liver, reach to the spleen, reach to the lungs. So the tumor will die together with the body, right? So what these nanoparticles did, they found out that the blood vessels surrounding the tumor, and again, like Hadar asked, not all the tumor has this leaky blood vessel, but most of them has, basically accumulating the tumor because they are very small. So 200 nanometer particles can accumulate in solid tumors, specifically breast cancer in this case, without poisoning the liver and the spleen. So if half a liter was injected at the past, now you can inject 100 microliter, which is like 2 drops. But still, these two drops, only half a drop reach the tumor, the other go to the liver. So all the time, the nanoparticle will try to make things more specific. If you want to think of it, it's like making these taxis, these Uber things that can deliver chemotherapy, contrast agent, whatever you would like, to specific areas. And we had a problem. We cannot make the story personal. So if you want to target only leukocytes, you cannot do that. If you want to target only endothelial cells, you cannot do that. So at the end of my PhD, I actually debated if to go to MIT or to the largest medical center in the world in Houston, Texas. And I decided that, it's not me, it's Professor Yuda Folkman who said, we know how to cure cancer in mice. So I wanted to do it in humans. So I went to Houston Methodist Hospital. And for 4 years, I conducted my postdoctoral fellow under the supervision of several PIs there in the cardiovascular sciences, in the neurosurgery department, and the neurodegenerative disease department. And they taught me to think a bit different. So biomimicry, it's a word that represents the fact that we want to learn from nature how to do stuff properly. Nature, God, if you believe, is the best engineer. Trillions of patients, walking patients every day, trillions of years of experience. So if we can learn from nature how to do things right, maybe we can cause our nanoparticles to target cells specifically. In our surgery room, we mimic the elephant trunk using a robot named Da Vinci robot. In Japan, the fast bullet train mimic the kingfisher bird aerodynamics. In my lab, we look how cells in our body stick or target different cells or tissues and basically mimic the way they are doing it. When I'm saying mimicking is basically politely stealing their membrane proteins, which are the same receptor on the cells, and put it on our nanoparticles. And why do we need to do that? Because I don't know if you got the COVID vaccine, which I'll touch base in a second about that, but basically this is what we do. We mimic the ways antigen presented in our cells. So to make things right, I will ask a question. Have you ever got bitten by a mosquito or a bee? Of course you are. And then you have inflammation in your body, and inflammation in Latin is fire. This is why it's red, right? It's burning. And then what happened? We all know that white blood cells arrive and fix it, right? But let's ask a very honest question. How white blood cells target inflamed areas? They don't have Waze, they don't have any compass, they don't use GPS, but for some reason, these white blood cells manage to target inflamed tissues. Does anyone in the audience want to take a chance and explain us why white blood cells target inflammation?
Is it the shape of the antibodies or whatever that's causing?
Okay, so that's one comment. So Stephen, which already recruited to my lab, assume that antibodies are the one who attract white blood cells to the inflamed area. The answer is might be, not that I'm aware of, but I'm not saying no, because that's a very complex cascade. Anyone else?
They must send off a signal. The inflamed cells must send off a signal, right? That the white blood cells could read.
Awesome. Thank you, Sally. And I didn't text you, right? That's your own idea.
Yes, am I admitted to your lab?
Sally, you are always welcome. I told you, Stephen will be the first male scientist. You are joining the Amazon. We need to teach you how to survive in the desert, but we'll do that. So what's happening, basically, a mechanical or chemical triggering is basically irritate the endothelial cells. So endothelial cells are the cells who build your blood vessels. Once an endothelial cell feel this kind of irritation, it raises a lighthouse. Hey, I'm injured. This lighthouse is basically a membrane protein, a unique membrane protein called intracellular adhesion molecule 1, ICAM1. Our smart white blood cells, the leukocytes, have another kind of magnet receptor for ICAM1 that calls LFA1, leukocyte function associate antigen 1. When LFA1 is introduced to ICAM1, they stick to each other. So I asked myself, if I will mimic the way white blood cells target inflammation, can we make nanoparticles that target inflammation? If we will take this LFA1 membrane protein and put it on my nanoparticle, will they target inflammation? And why it's important? Because inflammation is the beginning of all the bad things, all the Pandora box in the nature. Atherosclerosis plaque, cardiovascular disease start with inflammation in the endothelial cells. Traumatic brain injuries start with inflammation in the endothelial cells. Triple negative breast cancer start with inflammation of the endothelial cells. Mosquito bites, malaria, gram-negative bacteria, and the list is so long. So if we will manage to create an Uber black taxi that know how to target specific inflamed areas, we can decide what we want to encapsulate in it. Contrast agent for MRI and CT, drugs for tumor, mRNA for vaccines. So what we did is very easy. We cultivate leukocytes in my lab. When you come to my lab, hopefully, guys, and next year we're celebrating the centennial of the Technion. So please, tell me if you want to come to the lab. Sally already been there. Most of the ATS guy already visited the lab. I'll show you how leukocytes look like. So my team basically cultivate the leukocytes. We extract their membrane protein. And then we have a microfluidic device that assembles them as a nanoparticle. We can make 10 liters in less than a day. Just to put things in perspective, when you got vaccinated for the corona, you got 100 microliter shot. 100 microliter. So multiply by 10 is 1 milliliter. Multiply by 1,000, it's a liter. Multiply by 10. I'm talking about million patients that can be injected in a day by making the particles in our lab. And then we took this nanoparticle and started to test if they can target inflammation, both in vitro and in vivo. And you know, I'm talking about the COVID vaccine because I want to show you how we make the particles in the lab. So who got the COVID vaccine in the audience? Perfect. Let me show you now how we fabricate it.
Got the vaccine.
Yeah.
So look how we fabricate this thing. We have a chip in my lab, left inlet, the mRNA, the same components that express the protein, the spike protein in your body. In the right inlet, we have lipids. This genetic cargo is charged negatively. These phospholipids, which are molecules that we have in butter, we have in olive oil, and are FDA approved, are cationic charged. They're positively charged. When minus and plus meet together, they stick to each other. So look how the particle is formed. And hoping I will be the first one who will show you what you were injected with. You will see the vaccine with your own eyes now. And this is how we make it in my lab as well. So we mix it together. This chip can make, as I said, 10 liters. So here you go. Here's the negative lipids surrounding, the positive lipids surrounding the negative genetic cargo, forming the COVID vaccine. This is one nanoparticle. You were injected with 100 microliter, assuming 10 in the order of 23 particles per ml. We can connect several of these chips in parallel and have more than 10 liters. We can make 100 liters. So if Ebola type F starts in Africa, we can vaccine the whole Israeli population in a day if someone will provide us with the mRNA. And again, everything of this is in my lab and you are more than welcome to come and visit us. We look at our way of fabricating particles like Lego bricks. The physicians, which know better than me the disease symptoms, will tell me what they want to encapsulate and what they want to target. And I will build it bottom up using the reactor I showed you. Long story short, in front of you, you can see endothelial cells in green. In red, you can see my nanoparticles. And we inflame these cells. So basically, we demonstrated here in my lab that leukocyte biomimetic nanoparticles can target inflammation better than the normal formulation, than formulation without a membrane protein. Then we took a mouse and looked at these nanoparticles in live imaging. And look how fast they circulate in the blood. So basically what you see in front of you is in the green blood vessels are the blood. These are the blood vessels. And look how fast and with high concentration these blood cells are circulating. And the answer for this is because these cells are like Trojan horse. The immune system thinks they are white blood cells because they have the membrane protein of the white blood cells, so they don't touch them, in comparison to any drug or any particle without the membrane protein. So by using membrane protein of white blood cell, we managed to target inflammation in vivo and escape the immune system. We did it in two different animal models. The first one was the local inflammation of gram-negative bacteria. So we injected LPS, which is the same sugar that causes inflammation in humans, to the right ear, and you can see how the particles target the ear. So in the future, we're going to put anti-inflammatory drug inside it and treat the inflammation specifically without poisoning other parts in the body. And this is a triple negative breast cancer example. And as I mentioned you before, our particles target the tumor better. So at the past half a liter, then 100 microliter in the 90s, hopefully in several years, it will be 1 microliter, which is basically like getting a sneeze by someone in the New York subway, right? What are we doing next? So we really try to like push this into the clinic. And this is very challenging because, you know, being an assistant professor, you have a lot of responsibilities and making money out of startups, it should be one of them, but it's not at the beginning. Because, you know, we want to make tikkun olam. That is how I was going in my grandparents' house. You need to do some good things in this world. The money will come if you do good things. So in front of you, you can see human, I think it's human or rabbits. I cannot really remember. But basically, guys, white blood cells are white. Look at that. That's a white blood cell of a blood sample. And this is the red cells. And in the middle, you can see the platelets. So we collect blood from samples, from patients. We collect the white blood cells. We extract the membrane protein. And we make a personalized leukocyte, biomimetic nanoparticle that can target inflammation. And why is it good? Because we took rabbits, we feed them with peanut butter for 6 months, and we started to inject them with this inflammation targeting nanoparticles with an MRI contrast agent in order to detect early forming of soft arteriosclerosis plaques. You will see in a second how in this rectangular, yellow rectangular, the blood vessels become white. This was the first signal that our nanoparticle target an early inflammation in the blood vessel of this poor creature. But basically what I'm going to imply now is that in the future, a patient with a bad genetic history can go to the physician and with a non-invasive MRI scanning, the physician can tell him, listen, buddy, either you change your diet or in several months we will have to catheter you, or put him under restrictions, or put him under a specific diet components. But basically, this early detection can be used not only for cardiovascular disease, but also for early detection of cancer. And as you know, this is super important. Okay, second story is ending now. Any question? Okay, guys, am I talking too fast? Or my Hebrew accent is confusing?
Too fast.
Thank you, Paul. I'll do it much slower. Okay, third story starts now. So I give this spiel in Texas, and this awesome Jewish family, American Jewish family, by the way, invite my family for Shabbat lunch. And we are going to them for Shabbat lunch, sit in the table, and their kids start with this kind of symptom.
My bedroom.
Which I did not recognize at the beginning because I'm not a physician, but my wife, may she be blessed, Noah, she's an occupational therapist. She's working with autistic children. So after we finished the lunch and thanked the family, she explained me all about the Rett syndrome. So Rett syndrome is a neurodegenerative disease that afflicts 350,000 kids worldwide. It affects mainly females because it's a mutation in the X chromosome, and the males usually die in birth. They don't have any cure, and these poor girls suffering from the symptoms of cerebral palsy, Parkinson, epilepsy in one little girl. There is no cure for Rett syndrome, and unfortunately, after 24/7 care at their house, they die at the age of 40. I know patients in the age of 50, but unfortunately, there is no cure for them. The family asked me a very honest question. Can you target neurons? And can you deliver the non-mutated protein to this neuron? And this is a very honest question of a family that want to take care of their kid. Neurons are not easy to target. It's not like tumor. It's not like endothelial cells. They are very, very patronizing cells. And I never touched neurons in my life. So maybe I will ask the audience, have you ever cultivate neurons in your lab, in your house? So I'm guessing not, but the first thing I did after this lunch is going to my lab and started to grow human neuron cells. And this is how human neurons look like. In green, you can see the neurons. In blue, you can see the nuclei, I'm sorry. And the first thing that one can see in his eye or her eye is that they are very dense, right? They're very sticky. When you try to take neuron cells with your pipette, the first thing you will notice that they are acting like a glue. When you take a microscope and Western blot and start to analyze this connection, you find the same thing I showed you with the leukocytes, but with a different receptor. Each neuron has membrane protein by the name of NCAM1, neural cellular adhesion molecule 1. NCAM1 on one neuron basically connects to NCAM1 on another neuron, creating a neural to neural cellular connection. So long story short, guys, I did what I did before. I mimicked the way neurons stick to each other. I took their membrane protein, tossed them on a nanoparticle, created a particle named neurosome, which is well patented all around the world. And this neurosome started to target neuron. And you can see in front of you the results. In red, you can see the neuron biomimetic particles. In green, you can see human neuron cells. And you can see for the first time how particles target neuron. And this neuron targeting was a paradigm change in the neurodegenerative disease world, because for the first time ever, someone managed to target these bastards. So basically, we have now a taxi that can target neuron specifically. So the first mission was complete, and as a good executive officer, now you look at the second stop. Now we need to demonstrate that we can deliver an mRNA that will cause the expression of a healthy protein. And that was not easy at all, by the way. So what we did in front of you, you can see cells. This is the gray thing you see in the background. In red, you can see the nanoparticle. This nanoparticle has mRNA encapsulated inside it. So the test is very easy. If the cells in front of you will manage to express a green fluorescent protein, so they change the color to green, this is a signal that the spike protein was expressed in the case of corona, or the non-mutated protein in the case of this poor syndrome. I want you also to pay attention to the timeline here at the bottom, because this is the real answer for all the guys who say that by getting the vaccine, we modify the DNA, we alter the protein presentation. The protein will be presented for X amount of time and then will disappear. So without further ado, here you go. So we cause the cell using our neuron biomimetic nanoparticle to express the protein. And as I promised, after 2 days, the protein disappeared. So all the anti-vaxxers that really believe that we are modifying your protein components, guys, send me a text message and I'll send you the movie to shove it to their face, okay? So what we offered at the beginning was to take this nanoparticle and inject it to the cisterna magna, to the spinal cord fluid of this patient, which is not a very easy route of delivery, especially if you need to do it 2-3 times a week, right? And in this time, I went back to Israel. I finished my postdoc. I went back to Technion, to the chemical engineering department, the Wolfson chemical engineering department. And what we started to do with my team is to think about different routes of delivery. And what we started to build now, and excuse me for not elaborating on it because the patent is written in this day, right, is we created the sniffosome. So just imagine that in the future, you can go to your physician and instead of being injected with a needle, you can just sniff the nanoparticles. So what you see in front of you for the first time is the preclinical results. I mean, we tested in mice, that you can take mRNA vaccine and sniff it. And suddenly these proteins start to be expressed in the brain. So one might ask, wait. We know that the brain has a barrier, the blood-brain barrier. How come the nanoparticle crossed this barrier? And to the ones who don't know, the blood-brain barrier protects the brain from circulating things in our blood. So viruses and bacteria cannot penetrate the brain while you guys are sick in flu or something else. This is how the brain protects itself. However, the olfactory bulb in the brain sits right here, you can see it here, sends the olfactory neurons through the intranasal bone. These neurons cause 300 nanometer holes in the bone. So if you will make particles that are 80 nanometer, like our nanoparticles, they will cross to the brain. And the second we saw these results, I told my students, stop. Now we start to work on Parkinson, Alzheimer, and ALS. Because we now developed a method, not only us, by the way, And if you ask me, I think Moderna, AstraZeneca, and Sanofi, and Pfizer are trying to do the same now as well, a way to deliver mRNA nanoparticles to the brain without inject them systemically, which I found very exciting, by the way, because my daughter hates to get vaccine. So that's going to be a really nice way to deliver it. Just to wrap up, God is better than us. Nature is super smart. And this is how the coronavirus look like. And this is how the vaccine look like. So while the coronavirus is really packed, very professional, you see like high abundant concentration of genetic cargo and spike proteins. And this is only 20 nanometer. Our nanoparticles are 160 nanometer and look like a Subaru compared to a BMW or a Dodge Wrangler, right? So what I want to tell you guys is we have to be modest. We have to improve. However, it was enough, right? The COVID vaccine saved humanity. We must say that. And this is the first lesson. We have how to improve. The second lesson, that science should be spoken in lay terms. If we will continue to patronize in the academy or in the hospital, things that the audience will not listen, or will follow our commands, that's a big mistake. So what we are trying to do now is just basically speak science in lay terms in order for everybody to understand. As I mentioned before, our lab website is in front of you guys. You can just take picture of the screen and the QR code will send you directly to our lab website. All the stories I told you and many more is there, very categorized by subjects. And I have to say thank you to my awesome team. You can see the list of them. They are great scientists. I think this is one of the strongest resources Technion has. We have bright students. In our microcosmos, we have the Amazon. And of course, I want to thank all the funding agencies. We had very luck during the past year. We managed to recruit a lot of money that support all this kind of research. And I want to thank you guys. And if you have any question, I'll be happy to take. Thank you.
Thank you so much, Assaf. That was really fascinating.
Yeah.
Does anyone have any questions for Assaf? David, you're on mute, so unmute yourself and feel free.
Yes, thank you very much. This is on a slightly different, perhaps a very different subject. I had read a short report about a protein called soluble urokinase plasminogen activator receptor, which acts as a thermostat to regulate the activity of the immune system. Are you at all familiar with this, and would this have any interaction with or interception with the nanoparticles that you're describing as a way of dealing with atherosclerosis?
So David, thank you for the question. Unfortunately, I'm not familiar with this protein. Okay. I'll be super happy if you can send it to me because it sounds exciting, especially if it's a thermosensitive immune system triggering. I'm sorry, not my cup of tea, but I'll be very happy to be aware of.
Okay. And my other question, I was asking before after the first part of your talk, and I think you may have answered it. When you inject the nanoparticles into the circulation, how do they specifically attach and know where to go or attach to the tumor cells that you're trying to target? And I think you answered it in your second part, but I wonder if you could just very briefly mention how they know where to go or how the body knows where to pick them up.
David, thank you for a phenomenal question because I have 3 hidden slides on it. So I will going to show you exactly. Thanks to David, you got the unrevealed secret world data now. So I'm going to explain you a bit physiology. Don't hate me.
Just leave it the way it is. It's fine.
It's not a question, right? Okay. So a solid tumor is propagate very fast. It needs more nutrition and oxygen, right? However, it does not get that because the blood vessels are limited. So when hypoxia environments start to be created, the tumor cells feel that, the endothelial cells start to feel this hypoxia environment and start to secrete a hormone angiogenesis hormone, which his name is VEGF, vascular endothelial growth factor. And what happened there, as I explained to my students, it's like Bnei Israel escaping from the Egyptian in Egypt. That's what happened. The blood vessels are built very fast in order to supply oxygen and food to the tumor. And because they built it super fast, there are holes in the blood vessels. These holes are 300 nanometer, like I put you back in the intranasal thing. So whatever will be smaller than that will be targeting the tumor specifically. Add to this passive targeting moiety by the formation of inflamed endothelia targeting, you manage to increase the tumor association. And just because you ask how it really happens, I'll show you like a thyroid cancer model. Wait, I think I jumped on it. Okay, look at that. So I'm in green in front of you. You are seeing a thyroid cancer. I took my nanoparticle, inject them systemically using yellow marker, and see how the target tumor in live imaging. You see how the yellow nanoparticles are floating toward that tumor? So they're exploding the holes I told you before, and 24 hours after it, you will see this tumor change its color to greenish yellowish. This is the same thing with sepsis or inflammatory bowel disease. Look how the red nanoparticles stick to the inflamed blood vessels, right here. You see how they stick to the inflamed blood vessels? So these blood vessels are inflamed because of the disease. My nanoparticles know how to target this inflammation using their marker. Thank you for the question, David. Geoffrey?
You mentioned earlier that nature had tens of thousands of years lead time on scientists. And with respect to mRNA type relief, we've been doing that for 10 years, maybe 15 years, something like that. And your lab is clearly leading and doing that. But the beauty of science today is that it's easily shareable between labs. I'm not trying to take your Nobel Prize away by any stretch of the imagination, but how many other labs are doing similar type things around the world?
So I love the question.
And not as well as you, but they're doing similar things.
No, they're much better. Trust me, much better for sure. I'm young and rude. They have years of experience and tons of funding. I will give you an exact answer, okay? And you know why I will give you an exact answer? Because this year I'm going to be the chair of the largest control release society conference in the world that will be held in Las Vegas in July 13. MIT, Harvard, Stanford, UCLA, Caltech, Aachen, Jülich, Stuttgart, Technion are going to pretend this one. We have 1,500 participants. We have 300 principal investigators. Assuming that another 300 did not sign in, or visa immigration issues, they cannot come to the States, I will say that I'm pretty sure that there are at least 1,200 labs in the world that are doing drug delivery. However, each lab has its own shtick. I'm using the membrane protein to target inflammation. Other labs use antibody. Other labs will use a short peptide. Other labs will use even polymer and not lipid nanoparticles. Some labs use cellular therapy. So I think the drug delivery world is really interesting now because we don't try to invent new molecules, new drugs. We just try to make it better. And I think by using FDA-approved vehicles with small modification, we basically can utilize drugs that proved as toxic or non-efficient using our system. So the competition is tough, but hey, that's what makes us better, right?
Yes.
Thanks, Geoffrey.
Hadar, do you have a question? You're muted.
Yeah, so is this currently being used as a therapeutic or is it still in the research stages?
So thanks, Hadar. So all the things I showed you, sorry, let's split it. So the collagen, the Hamas nanoparticles were patented by Technion in 2018 and are now well acknowledged patent all over the world. It's stuck in the preclinical trials, I think, due to two main reasons. First, I left for my postdoc. Second, we did not establish a company. When I say we did not establish a company, it's Professor Avi Schroeder and myself. I'm Avi Schroeder's first PhD student, which I'm very proud to say. The leucosomes, leukocyte biomimetic particles are well internationally accepted patent. You can find it in Google Patents. And we already finished preclinical trials in mice and rabbits. And I think now Houston Methodist Hospital Technology Transfer Office is trying to find people to invest in pivoting this kind of technology. However, this patent is split between myself at Technion and Texas. The neurosome were patented at Texas, but now we are submitting other additional comments to this patent at Technion. Sniffing nanoparticles is something that we are still working on it now as a patent at Technion. And unfortunately, all of this stuff are stuck now in the preclinical trials. So it will take them at least 5-7 years to be approved by FDA, I'm hoping.
Thank you.
Thank you, Hadar.
Thank you.
Baruch?
Yes, thank you, Assaf. A very nice presentation and some very excellent work. I worked many years at Moderna, so I'm very familiar with lipid nanoparticles. But I think the future of use of lipid nanoparticles is more going to be in the delivery of gene editing, Cas9 or other forms, because as you mentioned before, for either enzyme replacement or for protein replacement, the frequent administration that's going to be required with mRNA delivered LNPs is going to be too much of a barrier. You can't deliver, certainly not to the CNS, but even peripherally, to have to deliver every other day or 3 times a week. It's just not going to be feasible. So there has to be a different way. But for gene editing, exactly what you want is tissue delivered short duration expression of a protein. So how much have you started to do any work with delivery of Cas9 or Cas12 or any of the editing enzymes yet?
So Baruch, thanks for a great, super professional question. I just want to make it clear for all the other audience. So as you know, CRISPR-Cas9 was, we had 2 Nobel laureates, right? We had Duadana and Peltier that won the Nobel laureates on CRISPR-Cas9. CRISPR-Cas9 is a mechanism learned from bacteria how to edit specific genes in our body. So if I'm providing the tissue with temporarily healthy protein, this kind of editing is a one-time job. The problem with that until the CRISPR-Cas9, people have used AAVs. They used viruses. The problem with viruses is that they might be toxic to the body, and they transfect all the cells in the body. They don't choose, they transfect everything. So the LNPs with the specific targeting can actually answer this question by targeting specific cell population. Regarding what you asked me, if encapsulating CRISPR-Cas9, the reason I think CRISPR-Cas9 is not being yet utilized, and again, it's my opinion, my perspective, in the clinics, is that we cannot encapsulate it into a lipid nanoparticle. The mRNA length of Cas9 is huge. Green fluorescent protein is 120 bases. I want to say the Cas9 is almost 2 orders of magnitude bigger. If someone will manage to encapsulate Cas9 inside the lipid nanoparticle, that will be a blockbuster. Professor Zeng from MIT just published a huge breakthrough in this world. So he used a bacteria mechanism to inject this huge mRNA Cas9. But Baruch, you're right. If I will find a way using a polymer or lipid to encapsulate mRNA of Cas9, I think that's the next step. You add a targeting moiety, you target specific cell, you added the DNA of these specific cells and not the other cells. So if you want to edit neurons, you will edit neurons, but not astrocytes. And I think that's really exciting. I think we are living now in a very exciting time. We are going through this direction, and I think COVID helped us a lot.
Well, it is already, the mRNA for gene editing is already being delivered by lipid nanoparticle to liver. So that's possible to do. There's a company called Intellia, and I founded a company called Verve that are delivering gene editing to the liver. So that's possible to do. But obviously, non-hepatic delivery of LNPs is much more challenging. So if you can do that in a tissue-specific way, then that would be very interesting.
So I will just add to that, you're right, 80% of the injected LNPs go to the liver, specific to the Kupffer cells, by the way. Hepatocytes is new to me. By adding membrane protein, as I showed before, leukocytes, we just demonstrated that the Kupffer cells uptake, it's much lower. However, we never delivered something that will edit the genes. We just added an mRNA that expressed for 48 hours and then disappears. So if you would like to discuss how to deliver something to non-hepatic cells using mRNA lipid nanoparticles, biomimetic lipid nanoparticles, I have several very nice proof of concept. And you just saw the intranasal mRNA delivery. We saw it in the brain and in the kidneys, but not in the liver. So if you want to speak more on that, I'll be very happy to talk.
Okay, yeah, we can do that, definitely.
Thanks, Baruch.
Does anyone else have any questions? You can raise your hand electronically or just speak out.
I have another question.
Go ahead, David.
When you mentioned that the cells in the solid tumors become hypoxic, it reminded me of in my earlier career when I was interested in the problem of hypoxia. I learned that Britton Chance had done studies of intracellular and extracellular PO2 in tissues, and was able to measure the intracellular PO2, which was something below 1, as I recall, but less than 1 millimeter mercury. Do you know, when you talk about hypoxia in the cell, do you know what the actual PO2 of those cells are, or are you judging hypoxia on the basis of just lack of blood flow?
So David, thank you again for very good question. So we measure hypoxia using basically a pH meter. So we basically induce pH meter measurement, acidicity measurement in the tissue. And there is a great paper by our team that was published that actually we demonstrate how bicarbonate delivery to hypoxic tissue can basically change the pH to the basis, kind of. I'm not an hypoxia researcher. I'm not a cellular therapeutic specific hypoxia evaluator. I'm just using engineered an instrument to measure the things I need.
Okay, thank you.
But look for this paper. That's a phenomenal paper by Hanan Abu Manal, Avi Schroeder, and myself that were actually demonstrated how delivering of sodium bicarbonate changed the pH in the tissue.
We have time for one more question. Stephen Richter, I think you have the last question of the evening.
Yeah, well, it's the slide that's up there now showing the team. It looks like all of the team members are women. Are there any men in the team?
So Baruch Hashem, I'm married and have 2 girls, Ayala and Tamara, and I learned in a very early stage in my life that they are better than us. No, I'm kidding. Yes, my team is composed mainly. Hey, Mark, I just see your face smiling there. What's up? I'm sorry, too long. Yes, so my team is composed from the Amazons. As I mentioned before, the Amazons are warriors and scientists. And it's funny because when I interview a student, we have several stages in my lab. So the first thing is drinking coffee with me for 10 minutes. If he passed the coffee interview, I send him to my team when he gives a scientific talk, and they interview him and eat lunch together. We eat a lot, as you can see. And unfortunately, when we interview males in Israel, I ask them right after the undergrad degree, guys, listen, what do you want to do with your life? And most of the answers like, I don't know, maybe I want to study, maybe I want to travel in India. However, when I interviewed this awesome team, all of them were like, I'm going to do PhD in your lab, then I'm going to do postdoc in Harvard or MIT, then I'm going to be a PI in whatever. And I'm like, and you know, most of them are already married and has at least 2 kids. I think we have an average of 2 kids in the lab. We try to recruit male. I'm looking for male. Actually, now I'm interviewing a postdoc, a Jewish postdoc from Princeton that considered to do Aliyah. And I'm like, hey, you are the perfect fit. They will love you. So please come to Israel. We'll do 2 things in one shot, right? We'll bring him to Israel and we'll add males to the team. We had one success. You can see here in the bottom, an undergrad student by the name of Dan Mansour, but he was graduated with excellency and the army stole him for a very special unit. So he will not conduct master's studies in my lab, but I'm super proud of him that he's contributing to Israeli defense in other ways. So if you know anyone that wants to make Aliyah, my lab is open, but he needs to pass the Amazon, which is not easy. Guys, thank you so much for your time. I'm hoping Celtics will kick their asses tonight. So
This
fingers
has
crossed.
been fabulous. I look forward to seeing you at your lab in Israel at some point.
Hey, you are invited. Just knock on the door and, we'll do you the coffee test.
Thank you very
Assaf.
much.
Hey, guys, shalom.
Thank you,
Take
everyone,
care.
for joining.
Have a good night,
Have a
everyone.
good night.